So in this video, we're going to talk a lot about different bond types that we would typically find in solids. Not liquids or gases, but typically that we would find in solids. Some of these are review, some of them are new. So we're going to talk about each type of bond, but more specifically, a big theme that we want to notice is how does structure, and this is something we've been working on a lot so far, how does the structure of a bond/molecule affect its properties? Okay, and we've done a lot of work with intermolecular forces and their effects on melting points and boiling points and vapor pressures and whatnot. We want to apply the same thing here to solids. So the first we're going to talk about are metallic bonds. Now we've discussed metallic bonds before. They occur in metals. Okay. So for example, if you have a bar of iron, Fe, how are the atoms of iron rearranged? Well, let's consider this as an example, an atomic view. Each one of these is an iron atom, Fe. And we know that each one of those atoms, if we drew the Bohr model, has electrons around the outside. In metallic bonding, the key thing to notice is that the electrons are delocalized. Delocalized, meaning they're not localized, they're not stuck to one particular atom. As you can see, each one of these blue dots, which represents an electron, has the ability to move amongst any atom that it wants. It can move around all these positive charges because it's attracted to every single one of them. There's this, what is often called a sea of electrons, because they can move in any different direction between all of these positively charged cation metals. So since we have this delocalization, what does that tell us about the properties of metallic bonds? Well, we've learned a few of them. They're very hard because the metal atoms are very rigid in their structure. Okay, but often they are malleable, which means they're bendable, a word that we need to know. Metals are bendable because while these electrons can move around, that provides some opportunity for the metal atoms to slide by each other a little bit, which allows a metal to bend. And they are good conductors of electricity. Since these electrons can move around, they're free-flowing anywhere we want. Electricity can pass through and around these metal atoms very easily. So those are metallic bonds. These are just when you have one element. In class, we'll talk about what happens if you have two metals mixed together. What's that called and what properties that affects. We've also discussed ionic bonds. So for example, if we have NaCl, we know this is made up of an Na plus atom, a cation, and a Cl minus atom, an anion. And since these have opposite charges, there's a force of attraction between these two, which forms the ionic bond. This is affected by distance. So we know as you make these atoms closer to each other, aka having smaller atoms, that's going to cause an increase in attraction, which I'm going to write on the side here, which means an increase in melting point. So when these metals and nonmetals get smaller and closer together, there's more attractive force, which increases melting points. So ionic bonds typically have high melting points and boiling points because these forces are very, very strong between them. And if we were to draw what the network would look like, we would have something like Na plus bonded to a Cl minus, to an to a Cl minus here, Na plus, and on, all these ions would have attraction between each other. There's a very strong attractive force, so it's very difficult to break, resulting in our high melting points, our high boiling points, etc. We've also talked about molecular covalent. This is what we typically think of when we say the word covalent. Greater than or equal to two nonmetals. Okay? So examples, CO2, CH4, these C6H12O6, sugar. These are all molecular covalent compounds. And we know that since they're all nonmetals, we have low melting points, low conductivity, and low boiling points as well. Okay? Now, one thing that's going to separate molecular covalent from what we're going to talk about next is how these atoms are bonded. So in CH4, for example, the Lewis structure of methane, this is what one molecule of methane looks like. It stands by itself. The carbon and the 4 hydrogens are bonded together. We then talked about how there's intermolecular forces, maybe with another molecule of methane, due to London dispersion forces or what may have you. But that's what's going to separate molecular covalent from the next compound, which is network covalent. Network covalent. When we're talking about network covalent, we're still talking about compounds that are formed with non-metals only. Still only non-metals, okay? However, what's different about them is how they're bonded. They're bonded in a network. And if you think about words of network, what does that actually relate to? Well, if you're trying to build your network as an individual, you're trying to meet a lot of different people. You're trying to be connected to a lot of different people. Think about you on social media, on your Instagram or on your Facebook or whatever. You are trying to be connected, have all these different followers, these different people. You're trying to grow your network. In a network covalent compound, atoms are trying to be connected to as many atoms as possible. Okay? And there's 2 ways this usually happens. Sometimes it's with just what's called elemental network covalence, or when we have 2 different nonmetals bonded together. And we'll talk about those examples in a second. The properties that we need to know for network covalent compounds, okay, is that, first of all, they're based on the structure of these compounds. And we'll talk about the structures in a second, but they have high melting points, okay? They're typically rigid and hard when they're in 3D. And again, we'll talk about what I mean by in 3 dimensions in a second. But these are the main things that we need to know about network covalent, which are also sometimes called network solids, just in general. So we want to make sure that we're aware of that language as well. Common examples. The first most common example of a network covalent compound or a network solid is graphite. All graphite is carbon. Atoms of carbon bonded together in a network over and over and over again. Graphite is formed in these sheets of carbon. So what you're seeing here, each one of these little blue circles represents an atom of carbon. Each black line represents a covalent bond between 2 atoms of carbon where electrons are shared. And as you can see here, here's kind of like one sheet. Think of this as like kind of a piece of paper with carbon atoms all covalently bonded to each other. Down here we have another kind of sheet of carbon atoms, and here we have a third. And what you may notice here is these dotted lines that represent intermolecular forces. Okay? There are these LDFs, these London dispersion forces, which we know that all covalent compounds have, in between these sheets. So as a result, because of this network of carbon atoms together and this network of London dispersion forces, graphite, this structure supports the idea that we have a very high melting point. Okay? However, graphite is actually very soft. It's not very hard and rigid. Think about common things that graphite are in, pencil lead. Okay? It's actually pretty soft. And the reason for that is because these sheets, each one of these sheets, they're not covalently bonded to another sheet. They're just held together with London dispersion forces. So these can actually move side to side. These sheets can kind of go back and forth amongst each other, which explains the properties of graphite being relatively soft. So when we're back here talking about elemental networks, this is what we're talking about, because we just have one element. We can also have network of more than one element bonded together, and the properties are going to be different based on that. So what we see here is another very common form of carbon, which is diamond, okay? Also made out of entirely pure carbon, but it's bonded together in a slightly different way. Here, each silver circle represents an atom of carbon, and every one of these atoms of carbon is bonded to 4 other atoms of carbon, okay? Boom, 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 in this never-ending network. All these atoms are all connected, on and on and on for as many atoms as we have. So as a result, this compound is very rigid and hard. In fact, diamond is actually the hardest known substance to man because of these extremely strong covalent bonds between each atom of carbon that exist in this network that kind of goes on and on and on forever. Well, until we run out of how big the diamond is, or how many carbon atoms there are. In addition to being rigid and hard, it has a very high melting point, okay? Because we have so many bonds to break in order to separate these carbon atoms to make, this into a liquid. It's going to take an extremely high temperature to melt diamond. In fact, diamond is actually formed, pure diamonds are actually formed over millions of years when carbon is put under high pressure and very, very high temperature. And that's what makes these pure diamonds that you guys all, or not you guys all necessarily, but people love to have and value and pay a lot of money for. Another super common example is silicon dioxide, SiO2. Okay? Silicon dioxide is the same thing. It's a network. Okay? But it's not just one element. We have silicon and 2 atoms of oxygen in that mole ratio of 1 to 2. So what we see here is the red represents silicon, and the blue here represents oxygen. So what you can see by the ratio is for every 1 atom of silicon, there's 2 atoms of oxygen. So here, in an atom of silicon, we have 2 atoms of oxygen on its side. For this atom of silicon, there's another 2 atoms of oxygen. Here, boom, boom. So the ratio fits the formula. But you can see that it's still bonded in this very similar network fashion, where every atom is bonded to every other atom in the compound. Silicon dioxide, therefore, has very similar properties as discussed before. It's very rigid, it's very hard, and has a very, very high melting point. So what you need to be able to walk with today, properties of network covalent compounds, the examples of graphite, diamond, and silicon dioxide, knowing their properties and how they relate to their structure, what we know about molecular covalent solids, ionic bonds, and metallic bonds as well.